Hello everyone. So in this video, we're going to be covering section 4.3 on definite integrals and Riemann sums. So we're going to begin with the definition. So in the last section, we talked about area, where we approximated the area under curves using rectangles. And we talked about how ideally we would like to have infinitely many rectangles to get the best approximation. So this expression here, if you recall, this expression there, that expression would be the area of infinitely many rectangles of width delta x. So delta x is representing how wide those rectangles are. And we are going to define the value of that area if we had infinitely many rectangles as the integral from a to b of whatever function we are integrating. We say that a is the lower limit of integration and that b is the upper limit of integration. And I just said of whatever function we are integrating, but perhaps a better way to phrase that would be of whatever function we are finding the area under it of. Now, when we do this, when we set up these rectangles, we start with a partition of whatever interval we're trying to find the area of the curve under. It would not matter if we were using left endpoints, right endpoints. We could use any partition, particularly because we are letting the number of rectangles go off to positive infinity. So later on in, I believe, the next lesson, we will learn a much simpler way to evaluate this expression, which is the same as this expression. But for now, we are going to be looking at, well, what is this limit as n goes to infinity of this Riemann sum? Kind of similar to how we started off with derivatives using the limit definition of derivatives, and then we eventually adopted some derivative rules where we were able to take those derivatives much more quickly. So we start off with a theorem here that tells us that continuity implies integrability. So what that means is that if we have a function that is continuous on some closed interval, then that means that it is also integrable on that closed interval. In other words, this expression exists. And remember, that expression, what we're calling a definite integral, that has these limits on it, is the same thing as the value of all of the area under the curve between a and b with infinitely many rectangles. So let's start and look at an example where we are going to evaluate a definite integral, and we are going to do it using this limit definition. It should be correct on your note sheet, but I want to change this upper limit here to 0. So I'm going to start off, first, to help us visualize this, I'm going to graph this function so we can see exactly what area it is we are finding. We have a simple function to start off. It's the line x plus 1. It has a slope of 1 and a y-intercept of 1 as well. So this is hitting the y-axis at the point 0, 1, and it's hitting the x-axis at negative 1. We are interested in the definite integral from -3 to 0. And so I'm particularly interested in what's happening from -3 up until 0. And 0 is, of course, the y-axis. I'm going to go ahead and draw a line there at -3. So what we want to know is what is this area, and this green area would be counted as negative because it is under the x-axis, and this blue area here would be counted as positive because it is above the x-axis. I will briefly mention that in a previous lesson we discussed evaluating the area of these regions just geometrically, because we're looking at two triangles here, and we know that the area of a triangle is 1/2 base times height. So this green area would be 1/2. The base from -3 to -1 is 2, and the height would be however tall this distance right here is. Well, if I take -3 and plug it into the function, I would get out -2. In other words, that's the point, -3, -2. So our height is 2. So 1/2 times 2 times 2 gives us 2, which would be counted as a negative area. And then this region here is another triangle. Area is 1/2 base. That base is 1 times height. This height is 1. So that's a positive half. So we had a -2 from the green region, a positive 1/2 from the blue region. So I am expecting my final answer to come out and be a -1.5, just for the record. Now let's actually evaluate this definite integral using the formal definition of it, the limit definition of it. The limit definition tells us that this area will be equal to the limit as the number of rectangles n goes to infinity of the sum from I equals 1 to n. And this is where we need to be putting the expression for the area of these rectangles. So if I imagine I start putting a rectangle in here, I'm going to put n rectangles in. Because we're putting in n rectangles, we know that the width of one rectangle would be 3 over n. And I know it's 3 over n because this total horizontal distance there from -3 to 0 has a length of 3. And if I want to put n rectangles in it, I would take that length of 3 and divide it by n to split those rectangles up evenly. And I did leave some space right here because this accounts for just the width of those rectangles, but we also need to multiply by the height of those rectangles. The height of each rectangle is going to be different, and it's going to depend on what x value we plugged into the function. So for instance, here, there's a first purple rectangle. If I come in and draw a second orange rectangle, so the x values, and remember, it doesn't matter what type of partition you're using. It doesn't matter if we're using left endpoints or if we're using right endpoints. So if you just want to assume that we're using left endpoints, this first left endpoint would have been at -3. The second left endpoint, at this point, you moved over one rectangle, so you're now at -3 plus 3 over n, because remember 3 over n is this 3 over n represents the width of that rectangle, so you moved over that much. And then I'll just do one more very quickly. If I put in another rectangle, I now would have moved over 2 rectangles. So this would have been at -3 plus 3 over n times 2. Right? Because we started at -3, we moved over 3 over n for the first rectangle, we moved over 3 over n for the second rectangle. So generally speaking, if I'm working with left endpoints, the x values that we're plugging into the function to get the height of those rectangles is -3 plus 3 over n I. Remember, I is indexing the rectangles, right? I is indexing which rectangle we are on. So we have our Riemann sum set up with our limit in front of it. Let's actually start evaluating this. So we have the limit as n approaches infinity of the sum from I is equal to 1 of n. I'm going to go ahead and simplify this expression. Remember, this means take -3 plus 3 over n I and plug it into the function f, which is this function here. So I'm going to go ahead and plug that in. It would give me -3 plus 3 over n I plus 1, and we're going to be multiplying that by 3 over n. So now we have the limit as n approaches infinity of the sum from I is equal to 1 of n. I'm going to be distributing here, so everything's going to get distributed. This 3 over n is going to get distributed into all 3 of those terms, giving us a -9 over n plus 9 over n squared multiplied by I plus 3 over n. So now let's actually look at evaluating these terms. And to do that, I'm going to drag over our summation formulas that we have seen before in a previous lesson. We can evaluate these term by term. Remember, this is indexed by I. There is no I that shows up there, and I'm going to have n terms in total. So that's like using this first part of the theorem there. So this would be -9 over n multiplied by n, because this -9 over n is essentially a constant relative to this sum, since there's no I in that term. Plus here, and I did drop my limit, which I do not want you to do. So let me go back and put my limit in. Okay, so we started off with -9 over n multiplied by n plus, I do have this 9 over n squared, which is like a constant. And then I have the sum of I, so I'm applying the sum to just that I term, and the sum of I is given here. It is n times n plus 1 over 2 plus, and then in the last term, we have no index of I. We just have a 3 over n, so if we add that up n times, I need to multiply it by n. And now let us start simplifying this. So some things will cancel out. For instance, those ends will cancel out right there and leave us with a -9 plus. It's not terribly important for me to distribute right here because we're going to notice a theme as we evaluate those. I'm going to leave that right there. I'm going to go ahead and cancel those ends out and have a +3 here. So remember, we're applying a limit, an infinite limit. We know how to take limits at this point. If I apply this limit term by term to the first term, we would simply have -9. If we apply it to the second term, well, the second term has some ends in it. But notice that the degree of the numerator is 2. The degree of the denominator is also 2. And we've seen when taking infinite limits, if the degree of the numerator is equal to the degree of the denominator, that the limit is equal to the ratio of the leading coefficients, which in this case would be a 9/2. That final term of 3 has no n in it, so this limit is simply going to be 3. So we are left with -9 plus 9/2 plus 3, which comes out to be a -1.5, just as we expected when we used geometry to calculate this netted area. And I say netted area because remember that the area under the x-axis is negative. Okay, so finishing up in lesson 19, when we were in class, we looked at the limit definition to help us find the area, where we had to look at the rectangles and use the summation and summation formulas and so on and so forth. Now we're going to be talking about area written as a definite integral. So if we have a function that is continuous and non-negative, you should be thinking that it is above the x-axis, because if the function goes below the x-axis, that's where it's having negative y values. The function's coming out negative on a closed interval from a to b, which are giving us the limits of integration, the lower and the upper limit respectively. Then we can find the area of the region that is bounded by the graph, the x-axis, and the vertical lines a and b, using this definite integral. Now, we're not yet talking about how to evaluate this, because so far the only way we have to evaluate this is using that limit definition that we were looking at in class with the summation and the f's of ci's and the delta x and so on and so forth. But for now, we're just going to do an example of writing the definite integral. So let's think about the function 3x minus x squared. This is a parabola that opens downward. It has x-intercepts at 0, 0, and 3, 0. This parabola looks something like that. This region here, between 0 and 3, that is above the x-axis, so that is non-negative. So the area of that blue region that I just shaded, that is under the graph, above the x-axis, and between the vertical lines of x is equal to 0 and x is equal to 3, would be given by the integral from the lower limit of 0 to the upper limit of 3 of the function 3x minus x squared dx. And if we wanted to actually evaluate that, that's us going back to that limit definition and looking at rectangles, but we're not going to look at that right now. Eventually, we will learn a much quicker way to evaluate that. Let's look at this next example here. I'm going to call whatever this function is, it's some sinusoidal function, either a sine or a cosine function. I'll call it f of x. What the function is not important right now. I'm going to shade a part of this function. I will shade right here, this blue region between 0 and pi over 4. If I wanted the area of that blue region, I would need to integrate from 0 to pi over 4. The order that we put that in does matter, of the function f of x. And then I'll put a dx on the end of that integral. But let's say I wanted to find the area that also includes this piece here, where the graph goes under the x-axis between pi over 4 and pi over 2. I would then need to add a separate integral that starts at pi over 4 and goes to pi over 2, but we have to be careful here because this orange piece of the graph is negative. And so if we're looking for area, we would want to take the absolute value of the function f of x and then I'll put a dx at the end of that. So we're adding the absolute value in there because that piece of the graph between pi over 4 and pi over 2 is under the x-axis. And again, we'll eventually, later next week, we will see lots of examples of us actually evaluating these definite integrals, but for now, we are not evaluating them, we're just writing them. These ones we will evaluate because it'll be very simple for us. In class, Aiden mentioned something about the shapes that we were finding, the regions that we were finding the area of were shaped like two triangles. And so he brought up the point of, oh, couldn't we just use the formula for the area of a triangle? And that's what we're going to be doing. Something similar to that's what we're going to be doing here. So this says to sketch the region corresponding to each definite integral and to use a geometric formula to evaluate it. So first I'm just going to sketch what the graph of 6 looks like. It's a horizontal line. Just runs straight across like that. And we're interested in it from -2 to 3. So the area that we're finding the region of is this area in here, which is a rectangle. And the area of a rectangle is equal to length times width. The length of this, I'm looking across the base here. This has a length of 5. The width of this, looking at the height of this, how far tall this goes. Remember, this line is up at 6. So this has a height of 6. 5 times 6 gives us a total area of 30. Looking at part B, we have the function 2x minus 3 from 4 to 8. I'm going to go ahead and set up some axes and sketch what that graph looks like. Graph looks something like this. This function, 4 is somewhere over here, and 8 is somewhere over here. Because I know that this function is going to actually be hitting the x-axis at 3 over 2. So this is actually hitting it like 3 over 2. So let's see what the function value is when, I'm going to make this line just a little bit longer so I'm not cutting off my 8. Let's see what the function value is at 4, and let's see what the function value is at 8. So when we plug 4 into the function, we get out 5. So this is the 0.45. Because 2 times 4 is 8, and 8 minus 3 is 5. And I'm plugging them into this function, so help you see that a bit easier. If I plug in 4, we get out 5. And if we plug in 8, 16 minus 3 is 13. So at 8, this function is up at 13. So the area that we are interested in here is this area here. And that is a trapezoid. And the area of a trapezoid, you could also have broken it up, I suppose, into a rectangle and a triangle. You should get the exact same answer either way. Area of a trapezoid is 1/2 height, and then you add the two bases, base 1 plus base 2. The height of our trapezoid, or the height of our trapezoid is 4. Distance between 4 and 8. Base 1 and base 2, it doesn't matter which one you call which one, but your bases do need to be parallel to each other. And so let's get our parentheses put back in here. Base 1 can be this one, and base 2 can be that one, but the two bases do need to be parallel to each other. Base 1 has a length of 5. You can see that from the y coordinate that's on there. And then base 2 has a length of 13. So we have 5 plus 13, which gives us 18. Dividing that by 2, I'm just going to go ahead and stick that with the 1/2 in the front, gives us 9, and 9 times 4 gives us 36. And remember, we can always check these answers because we should be able to calculate that definite integral in our calculator and still be getting 36. A quick remark here, all of these integrals have the same value of 36. The first one is the exact same one that we just did. The only difference between the other two is that they're changing variables from x to t to z. Changing the variable of integration does not change the value of the integral. So it doesn't matter what you call the variable, as long as everything else stays the same. The limits on the integral, the upper and lower limit, and the integrand, what's on the inside of the integral, as long as those stay the same, the integral is going to have the same value. Now we have two special definite integrals. The first one says what's important here is that if you're integrating from a to a, if your upper and your lower limit are the same, then your integral is just equal to 0. Because if you think about it, think graph-wise. If this is a, and I'm integrating from a to a, I'm just integrating over a line. There's no region, like I didn't go all the way to B to have that area to shade. I went from A to A. And lines do not have area because they are one-dimensional and not two-dimensional. The second integral tells us that if we switch the limits of integration, if we go from B to A instead of from A to B, what it does is it gives us the opposite of the integral that went from A to B. And A is smaller than B in this case. So if you evaluate an integral from A to B, and then you switch your limits of integration, you will get the exact same value for your new integral, but it will have the opposite sign. Let's look at a couple of examples. If we were to integrate sine 3x from pi over 3 to pi over 3, our answer would be 0 because the lower limit and the upper limit are exactly the same. And then in that second example, let me look back at what we did in class together. In example 1, so I'm going to change this to a -4. I'm going to rewrite this one. The integral from, I'm going to change this to 1 to -4 of x plus 1 dx because I want it to match example 1 that we did. In example 1, we did example number 1. In example 1, we did the integral from -4 to 1 of x plus 1 dx. And as our answer, we got -2.5. So down here, we're doing the exact same integral. The only difference is instead of going from -4 to 1, we're going from 1 to -4. So the answer we're going to get out is going to be the opposite of our original answer. We change the sign. When you switch your limits of integration, your sign changes. And one of the last things we're going to talk about here is the additive interval property. I'm going to draw a quick little graph to just show you what this means. So let's say that we have a function, and I'll say this is A, and this is B, and this is C. And let's say our function looks like this. Doesn't really matter what that happens there. The integral from A to C would give us all of this here. All this theorem is saying, oh, I think I have these switched around. Switch these around, please. Put C in the middle and put B on the end. Okay. The integral from A to B would give us that entire area that I have shaded there. All this theorem is saying is that you could break it up and first just go from A to C and take this area and then add it to the area from C to B. That's all that's saying. And it didn't matter if the graph would have dipped under the x-axis as well. So just another graph real quick as an example. If our function would have looked like that. Then remember, when the graph is dipping under the x-axis, if you're not taking absolute values, you're not talking about area. You're talking about more of like a net area where we have everything above the x-axis coming out positive and what's below the x-axis coming out negative. But this theorem still applies in this case. We could still break this up and integrate from A to C, and then integrate from C to B. And that would still give us the total net area from A to B. Let's look at example 5. Let me erase this graph here. I'm going to sketch a graph of the absolute value of 3x. Looks like a V. There's -2, and there's 1. At -2, this is up at 6. And at 1, this is up at 3. So this definite integral here, we're talking about this region here and this region here. And I'm intentionally using different colors because this is technically, absolute value functions are piecewise functions. Because this line, let's use a different color here. This piece of the graph, this line here, is actually the line of -3x. That's the line y is equal to -3x. While the other half of the graph is the line of y is equal to a +3x. So if we wanted this integral from -3x to +3x, I just want to point out that this is the exact same thing as integrating from -2 to 0 over the first half, which is a -3x, and then adding that to the integral from 0 to 1 of the second half, which is a +3x dx. We're actually going to evaluate this integral. I'm going to use 2 separate triangle formulas. The formula for the area of a triangle is 1/2 base times height. So for that first triangle there, in red, the one on the left, we have 1/2. The base of that triangle is 2, and the height of that triangle is 6. For the second triangle on the right, the one in blue, formula is 1/2 base times height. The base of that triangle is 1. The height of that triangle is 3. So we have 6 plus 3 over 2, which is a 7.5. We have already seen examples of us using these properties of definite integrals. This is telling us that if you have a constant on the inside of your integral, you can pull it on the outside of your integral and continue integrating. The same way we do with limits and the same way we do with derivatives. The second one is telling us that if you are adding or subtracting on the inside of your integral, you can separate that into 2 separate integrals and then add or subtract them. The same way we do with limits and the same way we do with derivatives. So now let's actually look at an example of us using these things. They give us 3 integrals here, the values of 3 integrals there. Something is, never mind. Okay, I got distracted. So what I'm going to do is I'm going to go ahead and start breaking this up. I'm going to separate this into the integral of -x squared from 1 to 3 dx. That is just this first term here. In fact, let me be a little bit more coordinated. The first term here is the integral from 1 to 3 of just -x squared dx. Then I will subtract that second term, integrated from 1 to 3. And I'm subtracting because of the minus sign that was in front of the -6x. And then I will add the third term from 1 to 3 of just a 5 dx. Notice that all of the integrals have a dx. That does not do anything at the end, but you cannot write an integral symbol if you're not writing a d something at the end. And that something needs to be your variable of integration. Now I'm going to start doing a little bit of manipulation. I'm going to factor out that constant of -1 from this integral, which just leaves me with the integral of x squared dx, and the negative is on the outside. I'm also going to pull out the constant of 6 from the second integral. Pull that 6 out in front of the integral and just leave us with an x on the inside. And then I'll also pull this constant of 5 out and leave that on the inside there. And now we can Now we can actually start evaluating these integrals because they told us that the integral of x squared from 1 to 3 is 26 over 3. So just this part right there is 26 over 3. And I'll bring down the negative that was there with it. I'll go ahead and bring down this negative 6. They told us that the integral from 1 to 3 of x dx is 4. So I'm replacing that with 4. And then for the last one, they tell us that the integral from 1 to 3 of dx is equal to 2. So this is 2. And then we will just evaluate all of this. So we have negative 26 over 3 minus 24 plus 10. That's a negative 14. If I wanted to write 14 with the denominator, really, you could just put this in your calculator. I'm not even really sure why I'm doing this, but this is negative 26 over 3 minus 42 over 3. And a 26 and a 42 will come together to give us a 68. Okay.